We are going to embark on our last material. The last material is thermodynamics, but we kind of squeeze in a little tiny bit about waves at the end. So that's kind of all grouped together. But thermodynamics technically means the study of the flow of heat. But we're going to start out just kind of trying to learn what heat is, what temperature is, what's the difference between temperature and heat, because in English we get a little bit, I think, confused between the two topics. And some of the material that we cover in the next couple of weeks is also material that students have seen in chemistry. So if you've seen it in chemistry already, hey, that's good news for you, because it may be a little bit easier. And if you haven't seen it in chemistry, then it's good news for you whenever you take chemistry, because you will have seen some of it in physics. So it's kind of, 2-for-1 special, I guess. So let me get the whiteboard up, and then we can talk about temperature and heat. So we have basically two competing words. And I think that a lot of people in English get these concepts mixed up a little bit. And I believe it's because we have a word hot. And the word hot in English means something has high temperature, but it sounds like the word heat and hot. They sound similar. So they're related concepts, but a little bit different. And another reason why it's confused is because for a long time, people didn't really know what heat was. So the sort of old model of heat was that it was some kind of fluid. It was a mystical fluid that was, unseen, unseeable. We can't see it, but we can detect its presence. We know when it flows from one thing to another. And people tried really hard to find a way to sort of squeeze the heat out of an object so that they could have just a cup of this mystical fluid, and no one could really get it. So this mystical fluid is called caloric, which is just the Latin word for heat. We have a very different idea now, but how did temperature factor into this? Well, temperature was just the way that you could tell which way the heat would flow. So if I have an object that is high temperature and an object that's low temperature, I put them together, then the heat will flow from the high temperature object to the low temperature object. How do we know it's flowing? Well, we can see the effects of the flow. Things, when they lose caloric, they get smaller. And when they gain caloric, they get bigger. So that really was thought that if you had a chunk of metal and you heated it up, you could measure that it expands. And it was thought that it's expanding sort of like a balloon to make room for this fluid. And then as it cools, you put it into contact with something with a cold piece of metal, and the hot piece sort of shrinks, and the cold piece sort of, gets warmer. It expands as it gets warmer. And additionally, we can feel it when we touch something that's hot. We can feel something, right? We have a sensation, and that sensation is energy being transferred from the hot object to our hand. And if we touch something that's really cold, we get kind of a similar but opposite sensation of heat flowing from our hand to that object. It may feel just as bad. It may be just as painful, but we can feel it. We feel the flow of this heat, but it's not a fluid. Okay, it's not a fluid. The modern picture is that what heat is it's the kinetic energy of all the particles in a sample. So you've got a chunk of metal, and if it's cold, it's atoms. I don't know if you can see me that well if I'm too small, but it's atoms are sort of grabbing onto each other, and they're kind of wiggling around. They have energy, they're vibrating, and if it gets hotter, they start to wiggle faster. Okay, and if you make it hot enough, they wiggle so quickly that they break free, and this thing turns into a liquid. So that we've got these particles that they're sort of still sticking to each other because they still have a force of attraction that makes them want to bind together, but they have too much energy to stop. That's kind of like a 3-year-old, they just can't stop them. And then if you give them even more energy, they break free of each other. And that's like when you go off to college, okay, and you just leave the nest. So the heat is a measurement of the total kinetic energy of the particles in a system. Okay, so that's what it is. It's a measurement of the total kinetic energy of the particles. And when the heat flows from one thing to another, it means that some of that kinetic energy is flowing from one to the other. I'll kind of clarify that a little bit once I say what temperature is. What temperature is again, originally the units of temperature had no meaning. You just took 100 objects and you put them in order from hot to cold based on which way heat will flow when we connect them. But there's no real reason to believe that the difference between 52 degrees Celsius and 53 degrees Celsius is the same thing as between 152 degrees Celsius and 153 degrees Celsius. All we know is that it makes an order. Now, the modern understanding is that the temperature is a measure of the average kinetic energy of the particles of a system. So we say something is high temperature if on average its particles are moving really fast. Okay, but that doesn't necessarily mean that that thing has a lot of heat. It may only have 5 particles in it. And so the total amount of kinetic energy in that sample, because there's only 5 particles, is very, very low, but the particles themselves may be moving fast. Contrast that with something that has a lot of heat. Means that if you add up the kinetic energy of all of the particles in the system, it winds up being a large number, but that doesn't mean any of the individual particles are moving that fast. It could just be that there's a whole lot of them. Okay, so I like to use an analogy of money to try to help understand, the difference. So just imagine right now there's, let's see, we have 7 people in this virtual class, 8 people if I count myself in this virtual classroom, 7 students. And so if we were to look in each of your bank accounts, okay, and look at your bank account, or maybe just you keep your cash, in your sofa or something, I don't know, whatever, where your money is. If we would add up your total money, it's not going to be a very large amount, because I'm guessing, because there's only 7 people here, okay? If we went to a similar class, the same class at Mizzou, might have a couple hundred students in it. So if we add up all of the money that those students have in their bank accounts, it's going to be a lot more, okay, just because there's so many students. However, the average money in the bank account might be less because the tuition is higher at Mizzou. So those students are paying more money. And so, all other things being equal, they should have less balance on average in their account. But still, the buying power of a class of 200 students at Mizzou, if they pooled their resources, would be bigger than the buying power of 7 students at the community college, even though you're saving money on tuition, so maybe you have more money in your bank account. Okay, obviously that's not a perfect analogy, because you may be a secret billionaire just slumming it to want to take physics. I don't know. but you get the idea. Having a high heat has to do with just having a lot of particles. And even you can be cold and have a lot of heat. So let's just kind of make a little grid and try to get some examples. Things with high temperature versus low temperature and high heat. We use the symbol Q for heat. Let me put that up next to heat on our table. Okay, so we can have things that are both high temperature and high heat. An example of that might be the sun or a active volcano. Okay, so those things are both very high temperature, but there's also a lot of high temperature stuff, so it winds up having a lot of heat. You can think of having a lot of heat as could you melt a lot of ice with it? Okay, and that's not a perfect definition, but it's a decent way to think about it. You could dump a whole lot of ice in an active volcano and it would not only melt, it would just vaporize it. Okay. But there are also things that have a lot of heat that are low temperature. So there are things that would melt a lot of ice, but that feel to you cold to the touch. Can anyone think of something not as cold as ice, warmer than ice, but colder than you, that you could melt a lot of ice with?
The ocean.
Yeah, that's a great example. The ocean, most places, is pretty cold. You know, you got to go to special places where the water is fairly shallow and not mixing with the deeper ocean real quickly, and then you can find warm ocean. But I used to live in Seattle, and the ocean is cold there. You know, it's cold. You still get in it because it's the ocean and you want to get in it, but it's cold. However, you could take all of the ice in North America and you could dump it in the ocean, and the ocean would melt it all, and you wouldn't even be able to tell that the temperature of the ocean had changed. Okay, so the ocean is a great example. So why is it high heat? Just because it's big. There's a lot of molecules in the ocean, and even though the average kinetic energy of those molecules is low, there's so many that the total amount of heat, if you would, I mean, all of the, you know, the energy in the hurricanes we get is all energy that's just like heat energy from the ocean that sort of combines in a place and you know, is released into the atmosphere. Okay, how about something that would be low heat but high temperature, something that actually is very hot, its particles are moving quickly on average, but there's not a total amount of heat that's large. You couldn't even melt a single ice cube. Can anyone think of something that would be hot? If you measured its temperature, it would be a high number, but it doesn't have enough heat to melt one ice cube.
A spark, maybe.
Okay, spark is a good example. It's, you know, if you could measure its temperature, a match would be another good example. You light a match, the flame is hot, you put the flame on the ice cube and it just goes psst, and that's it. Just psst. There's a little noise and you barely notice anything on the ice cube. So a spark, a drop of like boiling oil or boiling water. Boiling water is hot, right? If you get in a swimming pool of boiling water, you're in trouble. But if just a drop of boiling water splashes on you when you're cooking something, it doesn't, you don't have to go to the hospital. So basically the point is the size. We're talking about things that are very hot, that is high temperature, but they're small. And so they don't have enough particles to have a lot of heat. And then finally, something that's low temperature and a low amount of heat. That's, you know, generally pretty easy. It's, you know, something like an ice cube. Okay, again, you can't use the melt ice analogy with ice cube, but I don't know, cup of cold water that's almost frozen, but not frozen yet. But things are colder than ice cubes. So ice cubes actually has heat in it because it's hotter than, say, dry ice. But nevertheless, it doesn't have a lot of heat unless it's big. An iceberg is very big, and so it actually can have a lot of heat in it, even though it's cold. All right, so we just want to separate those two ideas, the temperature and the heat. In order to measure temperature, we have devised a few temperature scales. Again, these scales historically come before we even know what temperature is. It's just a way of rank ordering things, how hot or cold they are, which way the heat will flow. But we have, a scale that you're all probably familiar with, the Fahrenheit scale. And this scale is built around two temperature points, two kind of fixed points. It's built so that the water freezes at 32 degrees on the Fahrenheit scale, and it boils. Does anyone know the boiling point of water? We all know the freezing point of water because we secretly are watching that temperature in the winter, hoping to get, if school's going to get canceled. We're hoping for snow. And but do you know what temperature water boils at? See, you only know this if you kind of learned it in a previous science class, because we don't really care what temperature water boils at. When you want to make some pasta, you just put it on the stove and you wait until it boils. You don't actually measure the temperature. But it's 212 degrees. So there's a total of exactly 180 degrees between the freezing point of water and the boiling point of water. So there's, this is the scale that we use in North America. When I was a kid, we learned about the Celsius scale, and we were told that by the time you're grown up, everyone's going to be using the Celsius scale. No one will ever use the Fahrenheit scale again. And I'm almost grown up, and we're still using the Fahrenheit scale. The Celsius scale, you probably have all learned about already in, middle school science class, or maybe elementary school and high school, and you're learning about it again now. But it does the same thing. It looks at the same two fixed points, the freezing point and the boiling point, and then it just tries to be a little more metric. Instead of having 180 degrees between those 2 points, we put just 100 degrees. So we have, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So the reason that these scales are built around the freezing and boiling point of water is because it's very easy then to build a thermometer. We just take a tube, we seal it with some mercury or some other, liquid in there, and we put it in like a mixture of freezing water, like ice and water floating. As the water is freezing, we will learn the temperature of the water sort of stays constant throughout that freezing process. And then once it's completely frozen, the temperature can go down and down and down. But we get it's a nice way of making something at a certain temperature. So you put your thermometer in the freezing water, and you just mark the line where the mercury goes. And then you put it in some boiling water. You'll see the mercury expands, and you'll find the place where, where the line goes then, and mark that. And if it's a Fahrenheit thermometer, you call one place 32, you call the other 212, and then you subdivide it, 180 times. If it's a Celsius thermometer, you call the first point 0 and the other point 100, and then you subdivide it 100 times. Again, there's no real reason to think that the size of those degrees are, meaningful. but we're just splitting it up into 100 little segments. But neither of these temperature scales is really very good, to be honest, because water doesn't really boil at 100 degrees C most of the time. If you are, you know, in Denver, which I don't know, maybe someone watching this is in Denver, then you're at high altitude and the water may boil at 95 degrees C. Water doesn't always freeze at 0 either. If the water has impurities, a little bit of salt or anything in it, then the freezing point is suppressed below 0 degrees C. So it's actually not a very convenient way of doing things, but if you don't really care what the degrees mean, if you're just trying to put things in order, then it doesn't really matter. So there's a third scale, third temperature scale, that is a little bit more more absolute and more universal. And that's the one that physicists like to use the most. Although, to be honest, we'll probably about 50-50 use Celsius scale and use this third scale. So the third scale is called the Kelvin scale. So the Kelvin scale comes from some experimental work where people made graphs of the pressure versus the temperature of a gas. If you take a gas and you measure its temperature and the pressure, okay, and then you change the temperature and see what happens to the pressure, what you see is you get kind of a straight line if you plot those points. Then you try it again, you take a different gas, a different volume of it, and you do this again, and you get another straight line, maybe with a different slope. And if you keep doing this, you always get straight lines. But if you do it enough, you realize that those straight lines, they all sort of share something. So let me try to draw straight lines through these points. So they all sort of point. I didn't do a great job. Maybe I'll do it starting here. They all seem to point at the same point on the temperature scale, no matter which gas, no matter how much of it, or what. It always looks the same. So what does that mean exactly? It seems to mean that there's some magic temperature at which, no matter what gas you're talking about, the pressure is going to be 0. So what does it mean for the pressure to be 0? It means that, we've got a box, a jar, something containing this gas. Where does the pressure come from? It comes from particles that are sort of flying around, and they're hitting the walls of the container and generating pressure. They're creating a force as they collide. So to have no pressure at all would mean that no particles are colliding with the walls of your container. And because we now recognize that temperature is measuring the average kinetic energy of the particles, if no particles, if not a single particle hits the walls of the container, it must sort of mean everything's frozen. Nothing is moving at all, which means the average kinetic energy of all the particles is 0. So that, for sort of theoretical or philosophical reasons, seems like as cold as it can get. You can't get less kinetic energy than 0. And so if every single particle has no kinetic energy, that's as cold as we can get. That's the least average kinetic energy we can get. That's when the pressure would be 0. So this temperature is referred to as absolute 0. That's the magic temperature at which, no matter what gas you're talking about, according to these data, it should be perfectly frozen, not moving. Not even just frozen. I mean, a piece of metal is frozen, but it can still be hot, and its particles can be vibrating and still have a lot of kinetic energy, and you can get burned when you touch it. But I mean, even the particles within that solid are not moving. Okay, they're not even vibrating. So the temperature scale, the Kelvin temperature scale, what it does is it says we're just going to change are the location of the origin, so that all of those rays, instead of pointing at some place on the negative axis, that point would be negative 273, more or less. There's a little change, 273.15 or 16 or something. But I just like to round it to 273. It's around negative 273 degrees Celsius, and we rescale things so that that would be 0 degrees Kelvin. So when you do degrees Kelvin, you don't make a degree sign, you just write a big capital K. So 0 Kelvin is the same thing as negative 273 degrees Celsius. And then the size of the degrees on the Kelvin scale are the same as the size of the degrees on the Celsius scale, meaning that there's 100 degrees between freezing and boiling point for water still. And so we would say that water freezes at 270, positive 273 Kelvin, and boils at 373 Kelvin. So basically it's exactly like the Celsius scale, but everything has been shifted by 273 degrees. So in general, if we wanted to convert, the Kelvin temperature is equal to the Celsius temperature plus 273. Okay. Raise your computer hand if you have seen the Kelvin scale in a class somewhere before. So let's see, 1, 2, 3, 4 people, 5. Okay, most people have seen it. It's really not a big deal. It is almost exactly like the Celsius scale. So the question maybe is, how do we know when we can get away with using the Celsius scale and when we should use the Kelvin scale? And there's a really easy rule. I'll just write it in red here. We're going to use the Celsius scale when the formula, whatever formula we're working with, has delta T. Heavy focus on the delta, okay, when it has a delta. Because a change of 20 degrees on the Kelvin scale is identical to a change in 20 degrees on the Celsius scale. So in those cases, we might as well use Celsius. However, for the Kelvin scale, we use it whenever the formula has T, but not delta T. Okay, so all of the formulas in this class are sort of calibrated so that if you see just a T in the formula by itself, it's not a part of a delta T, then we better use the Kelvin scale. But if it's a delta T, we can get away with the Celsius scale. What do we do if we have temperatures in the Fahrenheit scale? Because that's, of course, the scale that we run into on a daily basis. Well, we have to learn how to convert from the Fahrenheit scale to the Celsius scale. And then sometimes we can just use Celsius. Sometimes we'll have to go one step further and convert to Kelvin. So this is kind of funny for me. I find it very hard to remember the formula to convert between Fahrenheit and Celsius. I know a lot of formulas, but this particular one does not like to stick in my brain very well. And so I usually wind up having to try to figure it out again whenever I have to do this conversion. This happened to me a long time ago when I was traveling. I was in Italy, and it was the summer, and I was going to a kind of a workshop, and I was dressed sort of, long sleeve button up shirt and long slacks and, kind of like, a little bit formal, but not super formal. And the airline lost my luggage. So this is like what I was wearing, and it was kind of hot on the train. And they don't have air conditioning in Italy. So I'm on the train and I see a kind of a bank, and it says the temperature is 40 degrees C. And I really had no idea if that's hot, how hot it is. I felt like it was kind of hot. So I kind of went through this mental calculation in my head, and I'm going to kind of show you the way I think about it. And it may help you if you're traveling someday and you may be in the same situation. So the thing is, I know that there's 180 degrees Fahrenheit that equals the same thing as 180 degrees Celsius. So that's a ratio of 180 over 100, which is 9/5. So the 9/5 constant kind of sticks in my head. I remember that constant. And so I know that the Fahrenheit temperature is going to be something like 9/5 the Celsius temperature, or it could be 5/9. That part I'm not always clear on. And then the zeros occur at different places. So you always have to either add or subtract 32 depending which way you're going. So what I do is I just sort of try to write down an equation that has a 9/5 and a 32 in it. And it depends which way you're going, if you're going from Fahrenheit to Celsius or Celsius to Fahrenheit. And then I check it, because if I put in 0 degrees Celsius, I should get 32 degrees Fahrenheit. So if I check that out, it's 9/5 times 0 plus 32, and that's equal to 32. So that actually checks out this equation, but it's not good enough for it to check out at one point only. So then I also check it at the boiling point. That would be 9/5 times 100 plus 32. And 9/5 times 100, let's see, 100 divided by 5 is 20, and 20 times 9 is 180, and 180 plus 32 is 212. So that checks out also. And if it checks out at 2 points, then it must be right. Okay, so I'm on the train in Italy thinking about this in my head, trying to figure it out. And then I go ahead and I plug in my temperature. We have 9/5 times 40 plus 32. And let's see, 40 divided by 5 is 8, and 8 times 9 is 72, and 72 plus 32 is 104 degrees Fahrenheit. And I'm being 100% honest here. As soon as I got to this point in the calculation, I started sweating like crazy. Before I got here, I felt like it was like 85, 88, something. And when I realized it was 104, I was like, oh my God, I can't believe it. And I had to wear the same clothes for like 4 days before my luggage was located. It was not a good way to start a conference. Anyway, you may find yourself in the same situation. You're traveling and you're familiar with Fahrenheit, and you see the Celsius temperature and you don't know how hot you should be. I might recommend you don't even try to figure it out. Just you're maybe better off not knowing. But here's another good way that you can tell how hot it is. Human body temperature in the Fahrenheit scale is, it varies, right? It's not really one number, but the sort of textbook number is 98.6 in Fahrenheit, and in Celsius, that's exactly 37 degrees. So if you ever see on the bank clock thermometer that it's hotter than 37 degrees Fahrenheit, that's hot. We don't like being in a temperature that's hotter than our body temperature, because we can't get rid of excess heat if we're in that situation. And if it's colder than our body temperature, we may not like it, but we can handle it a little bit better. On the other hand, if you go in the other direction, when I was there, I was a grad student at this time, so I wasn't presenting, so I was just there to learn. And I met this Swedish girl, and we got to talking about like the weather, and I said, how cold is it in Sweden in the winter. And she said, oh, it's not really so bad. Maybe -10, -15. And I'm like, what? -10? Are you, what? That's not that bad. But in Celsius, it's not really that bad. So it's really bad in Fahrenheit. But in Celsius, so if I want to find out what is -10, in Celsius, we can just, T Fahrenheit equals 9/5 times -10 plus 32. Let's see, 10 divided by 5 is 2, so that's a -18 plus a 32, and that's like 14, is that 20? Am I doing my math right? Yeah, 14 degrees Fahrenheit, which is cold. But it's not as cold as -10 or -15, the way it sounded to me. So I still think I prefer Italy, probably the weather there to the weather in Sweden, but I don't know. I haven't been to Sweden, so I'm going to go someday. Anyway, this is how you do it. If you want to go from the other way, if you have Fahrenheit and you want to know the Celsius temperature, that's actually what we have to do when we're solving problems. Then we have to do the algebra first, subtracting 32 from both sides. And then to get rid of the 9/5, we're going to multiply by 5/9 on both sides. So the formula going the other way is 5/9 times the quantity, T Fahrenheit minus 32. And that's how you do it. Now, on the formula sheet, I'm not going to give you both of these. I'm just going to give you the T Fahrenheit formula, and it'll be up to you to rearrange it and invert it. Again, if your formula has a delta T, we're going to want Celsius degrees. If it has just a T by itself, we're going to want Kelvin. Okay, so I know you probably mostly all know all of this stuff. But does anyone have any questions? Okay, so one of the things that we use to measure temperature changes, we use thermometers, is the thermal expansion of the materials. The mercury gets bigger, it expands when it gets hot, and it contracts when it gets cold. And this is not 100% universal, but it works for most things. Water is actually a very strange material. It's very unusual in that as water cools, it shrinks for a while. It shrinks, and then it shrinks all the way down to 4 degrees Celsius. And then when you go from 4 degrees Celsius colder, it starts to expand again. And that's why if you put something, like a glass bottle of something in the freezer, that if it's got water in it or a lot of water in it, then it's going to break because that water starts to expand as it freezes. Other liquids don't have that property, or most other liquids don't, but water is a little weird that way. So for most materials, it is the case that if we heat it up or cool it down, it experiences a change in length. And that change in length is proportional to the initial length, and it's proportional to the change in the temperature. So the way we write that one thing is proportional to, so this symbol here means proportional to. It looks kind of like an alpha with a really long tail, or maybe like 3/4 of an infinity sign. If you wrote an infinity sign and then you erase like the right hand 1/4. And the formula for it then is when things are proportional to other things, we say they're equal to those other things times a constant. So the constant that is used, this is a little bit confusing, is the Greek letter alpha. I know that looks a lot like my proportional to constant, but this is the Greek letter alpha, the one we use for angular acceleration. And it is called the coefficient of linear expansion. And it's a number that just tells you sort of the percentage change in length something gets per degree Celsius temperature change. So we'll try to put it in context with some numbers in a minute. But suppose I have an object and it has an initial length L naught, and then we heat it up. So I'm gonna So we heat it up, and as we heat it up, it starts to expand. So it had an initial length L, and it has a new length, or initial length L naught, and a new length L. The new length will be equal to the original length plus the change in length. So that is the original length plus original length L naught alpha delta t, and we can factor out the L naught, and we get L naught times 1 plus alpha delta t. So that's the formula. If we want to find the length something's going to be after we changes temperature, we have to know the rate of thermal expansion. That's this alpha, the coefficient of thermal expansion. We need to know how long it was to begin with, and then we need to know what kind of temperature change we're talking about. There's a lot of famous examples of thermal expansion sort of going wrong. There's a kind of famous one from St. Louis history, and that's the St. Louis, Gateway Arch. Probably some of you are local and have, when you're a kid, you go to the Arch and they show you a movie about the making of the Arch, and maybe someone among you remembers this. But when they were getting ready to put the last piece of the arch in, so here's the arch, it's like this, and they're getting ready to put the last piece in. They come in, and the last piece was like too big, didn't fit. And I mean, just imagine being the foreman of this project, and they've spent a couple years, putting this side up and putting the other side up, and then they get up there, and you're like the left side, you're just thinking that, oh, we started it 2 inches too far to the right. We got to move the whole thing, So somebody really messed up is what you're thinking. But they figured it out that what had happened is that it was a different season, from when they started. And so what happened is the two sides of the arch, it was a hot day. They had expanded. And so what they did is they got fire trucks out, and they started spraying the arch down to try to cool it off so that those sides would shrink a little bit and they would be able to fit the last piece in. I don't remember actually if the last piece was too big or too small. I'm just making a guess there. But at any rate, this kind of thing, it's a very small effect, but if you have a long object like the arch or a bridge, then the thermal expansion can be actually kind of catastrophic. The bridges also, if they're not built sort of keeping in mind that they're going to expand and contract, then when that happens, they're gonna break and fall apart. So they actually build bridges with these joints called expansion joints that have kind of teeth that kind of open and close. As it expands, they kind of fill the space, and then they sort of go in and out. And that keeps them from breaking in the extreme temperature changes. And I've seen some photographs of train tracks. When they lay train tracks, they leave gaps. You don't really notice it, but they leave little gaps between the metal rails. And if they don't, what happens is the train track gets hot, and all of the tracks try to expand, but there's no room to expand. And so they kind of wind up just buckling. Like you'll see this track, it's going, and then it just there's a weird curve in it because they laid the track too close to the pieces too close to each other. Okay, So any questions about this thermal expansion formula? So I'll write that name down, thermal expansion. Okay, so just, for the sake of it, let's imagine we have a steel tape measure. Lauren, you have your hand up with a question?
Yeah, I just had a question. So is this where you were talking about with the delta T, you would use it in Celsius?
Yes, exactly.
Okay.
Because there's a delta T in this formula, you can go ahead and use Celsius. But if it's, if it had just a T by itself, then we would have to go to Kelvin. Yeah, so suppose you have a steel tape measure that is 100-foot steel tape. But that is at 20 degrees C. And we want to know, how long is it at 40 degrees C? So you can imagine if you're in construction and you're building something, the fact that your tape measure on a hot day expands if it's a long, beam, you might mismeasure it because your tape measure got hot. Let's see what the new length is. So the L is equal to L naught times 1 plus alpha delta T. So alpha for steel, I think, might have to look this up. I think it's 12 times 10 to the minus 6 inverse degrees Celsius. So that the units are degrees Celsius to the minus 1 power. Those units are so that when I multiply alpha times delta T, I just don't get any units left over at all. Okay, so we get 100 feet times 1 plus 12 times 10 to the minus 6 times 20 degrees. That's the change in temperature. It went from 20 to 40. So that's a change in temperature of 20 degrees. So that is 100.024 feet. And then let's see, 0.024 feet times 12 inches per foot is basically 100 feet and 0.288 inches. So you gained like a third of an inch on your steel tape, which means if you measure something and you're trying to measure something to be 100 feet long, it winds up really being 100 feet and 3/8 of an inch or something like that, which may or may not matter to you, but generally in construction, you don't want to be off by 3/8 of an inch. Things aren't going to fit properly. On the other hand, if you're measuring a piece of steel, the piece of steel will have expanded also. So it actually might be just right. But if you're measuring copper pipe, the copper pipe's going to expand at a different rate from the steel tape. And so, it can be a problem. It's probably more of a problem for engineers to think about than construction workers. Okay, well, the same thing that happens with a length, like a steel pipe or a steel tape measure, also happens with areas. If we have an area, like a sheet of something, suppose it has an initial length, L naught, and initial width, W naught, and an initial area, area naught. And then we let it expand. So now it has an area and a new width and a new length. And we want to know, what's the rule for areas to expand? Well, the area is just going to be length times width. But the length has expanded. So length would be L naught times 1 plus alpha delta t. And the new width would be width times 1 plus alpha delta t with naught, W naught. And if I factor out the L naught and the W naught, what's left is 1 plus alpha delta t squared, because we've got two terms that are identical multiplied together. And that's equal to the initial area, A naught, times 1 plus alpha delta t squared. However, we can simplify this a little bit by making an approximation. If we would multiply this out, when we have something squared, we multiply it by itself and kind of FOIL it. And what we would get is a 1 plus 2 alpha delta t plus alpha delta t squared. But look at how big alpha delta t typically is. Because the alphas are really small numbers, like 12 times 10 to the minus 6, and the delta t's are not usually so big. I mean, even if we had a delta t that was 1,000 degrees, this would still be 12 to the minus 3 when we multiplied them. So the point is, alpha delta t is a very small number. So alpha delta t squared is even smaller, and we can generally ignore it. Not zero, but very small. We can ignore it. And if we ignore it, we get A equals A naught times 1 plus 2 alpha times delta t. And this thing that's 2 alpha, sometimes we use the Greek letter gamma, and it would be called the coefficient of area expansion. However, we typically won't see a table. So the alpha is a number we would find it on a table, just like we would look up densities of materials or something. We would look on a table and find the alphas, the coefficient of thermal expansion, of linear expansion for different stuff. We won't find a gamma on a table because we just find alpha and multiply it by 2 if we have an area. And that's what we just kind of showed here. Any questions about that? Suppose I have a sheet of stuff and I cut a hole in it. And then I heat it up. What happens to the hole? Let's just have a vote. So I see 3 possibilities. Either the hole gets, bigger, or let's see, I don't have room here, or it gets smaller, or there's no change. So who says, show me with your computer hand, who says you think the hole's going to get bigger when we heat it up? 1, 2, 3. Who says 4? Who says it's going to get smaller? 1, 2. And who says no change? I think that's already everyone now. Okay, so I think it's kind of interesting because I could really see it going either way, you know, I mean, just depending on how I think about it, but it actually only goes one way. And so the hole does get bigger. It gets bigger. So why does it get bigger? Well, it comes down to why things expand in the first place when you heat them up. You can think of the atoms in a solid as being connected by springs. And so if they're vibrating a little bit, those springs are kind of stretching. If they start vibrating faster, those springs start stretching more, so they're spreading out. Okay, and what happens is all of the particles want to move away from every other particle. So then we come to the particles around the edge of this hole. And you know, there's particles behind those particles too. So the particles around the edge, they want to get farther from each other. So if they move in, they get closer. So they don't want to do that. They basically, it's like there's a pandemic for particles and they just want to spread out and keep as much distance between them and any neighbors as possible. So what happens is when you heat it up, these guys all move backward to get away from each other. And then these ones, they start moving backward to get away from those other ones. And this sort of chain just keeps going all the way back. Okay, so the hole is going to expand. This is actually kind of useful for, you know, plumbing or other things. If you have maybe you have a nut that you can't get off of a you know, of a bolt or something, you can heat the nut up, and as you do, the size of the hole is going to expand and make it a little bit looser. Or maybe you want to go the other way. You want to make something so that no one can ever get it off again. So you can take a pipe that is a little too small to fit over another pipe, and then you can heat it up with a torch so that it will fit. And then you sort of slide the sleeve over the other pipe, and then when they cool down, you know, that outer pipe that was a little too small, it's going to squeeze down, and then you're basically never going to get that thing apart again without heating it up, and it's hard to heat it up without heating up the other pipe. So at any rate, this is that's the way it works. As we heat this thing up, the whole thing just expands, and that leads to the hole getting, you know, getting bigger. Now, I wanted to do one more thing, and this is, I'm going to offer you some extra credit. So I know, oh, I see you guys kind of like leaning in, like, ooh, extra credit. All right. Now you're speaking my language. Okay, extra credit. So we're going to do the same thing, or you're going to do the same thing that I just did with areas to find a volume expansion. So we want to find V equals V naught times 1 plus, in this case, we use the Greek letter beta. That's the coefficient of volume expansion. So we should get a formula like that, but we're going to try to work it out and see how beta relates to alpha. So what we do is we imagine we have a shape, kind of a 3D shape, and it has, you know, a length initially and a width initially and maybe a height initially. And then we're going to, you know, expand it. We're going to heat it up and it's going to expand. And so you're going to work this out on your own by saying that, you know, the volume is going to be L times W times H. And use the same strategy we used here, where we replaced L with sort of the thermal expansion formula for L, and we replaced W with the thermal expansion formula for W. You're just going to do that, but this time you're going to do it 3 times because there's L, W, and H. And so when you do it, instead of getting a squared here, you're going to get a cubed. And you're going to then have to FOIL out that cubed thing. You'll have to expand it by foiling it. Maybe you have to FOIL it twice. And once you do that, you're going to see a whole mess of stuff. But you then have to say anything that has alpha delta t squared or alpha delta t cubed, we're going to throw those away because they're too small. And you only keep the terms that have alpha and delta t. So if you do that, what you're going to find is that beta equals 3 times alpha. That's what you're going to get. So I'm asking you to prove that by using the same technique that we did to prove that the area expansion coefficient was 2 alpha. All right, this is not too hard. It's, you know, it's not too hard. It's a little hard, but not a lot hard. All right, any questions about the extra credit? Okay, so volume coefficients beta, you will find those in a table. There's a table, I don't remember which of our problem books, but one of the two has a table at the beginning of the chapter on thermal expansion. And it has a table for alpha. It lists alpha for a lot of solid materials, and then for liquids, it lists beta. Because liquids don't really have an alpha. When you have a liquid, it just comes as a volume. And so when you heat it up, maybe it's gasoline or it's water or it's, you know, motor oil or something. When you heat it up, it's going to expand as a volume. And so there are data there for that. So on the other hand, if you have a, you know, a metal or something, a solid material, but you want to know how its volume expands, you will not find it on the beta table. You have to find the alpha and then multiply the alpha by 3 to find the beta. Okay, so that's why we worked out this formula. This kind of reminds me whenever I talk about the volume expansion of the Great Boston Molasses Massacre. Have you guys heard of that? Nobody's heard of that? I can't believe that they don't teach the Great Boston Molasses Massacre in school anymore. But no, I can believe it. It's not very well known. But this is kind of a cool trivia thing. This is something that happened when Prohibition went into effect in the early 20th century. You know, there was sort of a date. This is the date, and before this date, you know, you can make alcohol, and after the date, you can sell the alcohol that you already had, but sort of grandfathered in, but you couldn't produce more alcohol, nor could you produce certain ingredients that people used to make alcohol, such as molasses. And so this particular company in Boston kind of went into overtime trying to make as much molasses as they could before midnight on this certain day. And they had this tank, it's basically like a giant water tower full of molasses that they just filled up. They kept filling it until midnight. They got it totally full. And because anything they had in the tank, they could still sell, and they knew the prices were going to skyrocket. And, you know, so that was like, it was kind of how people were hoarding masks and hand sanitizer about a year ago. It's like that. They knew there was going to be this gigantic scare that everyone's going to need it, and they could sell it for whatever price they wanted. So what they didn't think about was that at midnight, it was very cold. And so the molasses had sort of contracted, and they got to fit a lot of molasses into this tank. But the next day, when it got warm, you know, in the afternoon, the molasses expanded and it burst the walls of this tank. And basically this tidal wave of molasses just like went, I don't know, I can't really visualize a slow tidal wave of molasses, but it just sort of started, you know, like a blob of stuff going through the streets of Boston. And to my knowledge, no people died, but a lot of horses got trapped in the molasses and had to be put down because they couldn't extract the horses. You know, probably humans were able to get out of the way, but horses were like maybe attached to a buggy or something, or you know, whatever. And I think a bunch of horses had to be put down because of this. And apparently it took like forever for them to try to clean the molasses out of Boston, like years. It took years to really remove all of this molasses. And it like soaked into the ground so that like on hot days, molasses would like bubble up from cracks in the ground. And supposedly, when I first read this story, it said that people in Boston still think they smell molasses on hot days. But I have a friend who's from, you know, Boston area, who spent a lot of time in Boston. She had never heard of the Great Boston Molasses Massacre. So I don't know, probably you can't smell molasses, but it is something that happened. And it's just coming down to this thermal expansion. And this is actually a real problem, like on the industrial scale all the time. If you have a vat of a liquid, maybe a chemical, a dangerous chemical, and you fill it too much, and then the temperature changes, well, the material of the vat can shrink and the liquid will shrink. But if the vat shrinks faster than the liquid, then the liquid is going to overflow. And the same thing can happen when it heats up. If it heats up and the liquid heats up fast, you know, expands faster than the container, then it can overflow. So you have to kind of pay attention to this in industrial settings. All right. Any questions?
I'm on Wikipedia. Apparently 21 people were killed and 150 people were injured.
21 people? I think Wikipedia is inflating the numbers because it used to be much smaller numbers. Really, that's crazy. 21 people? Wow.
I used to live in Boston, so I Wikipedia'd it. I had never heard of this.
Never heard of it. Yeah, so interesting. Well, now you have to like contact your Boston people and see if any of them know about it, and just ask them if they smell molasses every once in a while. That's interesting. So, okay, so I'm wrong about how many that there weren't human fatalities. I thought that there were not, but apparently, wow, that's 21 people and how many horses?
Wikipedia says 150 people were injured, 21 people killed, and several horses were killed.
Oh, more people than horses?
I don't know if several is more than 21. Maybe they don't know.
Yeah, there might not be accurate records on the horses there. All right, anyway, let's move on. Thank you for sharing that. That's pretty cool. Well, I mean, it's not cool, but it's interesting to know. Okay, so the last thing I want to talk about, again, is a little bit of material that some people have seen in chemistry. And if you haven't seen it in chemistry, that's okay. We're going to get practice in it in this class. If you have, it's just a bonus for you. But if we take gases and we start to sort of experiment with them, we change the temperature and see how the pressure is affected. You know, I already showed you that graph. But there are other variables that we can play with, and we want to see how they're all connected. So if we increase the temperature of a gas in a container, you know, we get this trend. And that means that the pressure is proportional to the temperature. But I didn't tell you the fine print about this graph. This is only true at constant volume. So, you know, if you have a container sealed that makes a constant volume, then you'll find that there's this direct relationship between the pressure and the temperature. And technically, you know, if I'm using the Kelvin scale, then the lines should point right at the origin. Okay, they should just point right to the origin. If, on the other half, we graph the volume versus the temperature on the Kelvin scale, so this is at constant volume. If we do this at constant pressure, we also get straight lines. So we say volume is also proportional to the temperature at constant pressure. And finally, if we graph the pressure versus the volume at constant temperature, it looks like that. And if we are not sure about the trend, we can try to plot. It looks like it's 1 over v, but maybe it's 1 over v squared or 1 over v cubed. It's hard to tell. So if we do experimentation and plot it versus 1 over v, we find out that there's a straight line. And so this means that pressure is proportional to 1 over v at constant temperature. Or we could say PV equals a constant at constant temperature. So each of these trends have their own names in chemistry class. There's Boyle's law and Charles' law, and there's all these laws, okay? And but they can all be unified into one sort of master equation. So if we do that, we get the master equation, pressure times volume equals, well, it would be a constant times the temperature. But it turns out that that constant isn't actually constant. That constant actually depends on how much gas we have. So the final form of this is PV equals nRT, where the little n is called the number of moles. And it basically measures how much stuff we have in a weird unit that chemists like, okay? They like to measure stuff in terms of this weird unit. It's kind of like how a dozen is a weird unit. You know, why are eggs sold by the dozen? You know, I don't know. Farmers a long time ago had 6 fingers and toes. I don't know. I don't know why a dozen is 12. But I do know why chemists use this particular unit, the mole. 1 mole is equal to 6.02 times 10 to the 23rd particles. So that seems like a really arbitrary number. What it is it's the number of particles in 12 grams of carbon-12. So carbon-12 has 6 protons, 6 neutrons, 6 electrons. It's a very average kind of nucleus, an average kind of atom. And so it's just picked as sort of, gives you 12 grams of carbon-12 is sort of an average of 1 gram per particle. And so this is in some average way the number of particles in 1 gram of matter. You know, if you just took like nuclear particles, protons, neutrons, and electrons, and cram them together, 1 gram of them would have about this many particles. So it doesn't really matter, just like it doesn't matter what a dozen is. We just will use this unit sometimes, okay? We'll use the chemistry unit sometimes. The value of R, so this formula is known as the ideal gas equation. And this constant R is known as the ideal gas constant. So the value of R is 8.31 joules per mole Kelvin. Notice this formula does not have a delta T in it. It just has a regular T by itself with no delta. So what does that mean? What does that tell us?
Use Kelvin over Celsius.
Yeah, we have to use Kelvin because it wouldn't make sense if I put in a Celsius temperature like -50 for the temperature And that would somehow imply a negative volume or a negative pressure. Neither of those things makes any sense. We can't have negative temperatures on this equation. So we have to use Kelvin. So you can think of this formula like the master equation that connects the pressure, the volume, and the temperature. These three variables are intertwined. They're interconnected. And if I freeze any of them, if I say the volume is constant, well, then it looks like pressure equals a constant times temperature. So pressure and temperature are linear. They make a straight line. They're proportional. If I freeze the pressure, then it looks like volume and temperature are proportional to one another. But if I freeze the temperature, it looks like pressure times volume equals a constant. Now, the number of moles, that's typically a given number. We're typically given the number of moles, although sometimes we might just be told the mass and we'll have to compute the number of moles from that, okay? We will learn how to do that. But generally, it's not a variable, okay? It's a given, it's fixed in the problem. But what can change is the volume or the pressure or the temperature. And so what the ideal gas law is good for is for us, if we have some gas and we make a change to the gas, maybe we increase the pressure and we want to know, well, what's going to happen to the volume and the temperature in that case? Or maybe we increase the temperature while also decreasing the volume. So we heat it up and we squeeze it at the same time. What's going to happen to the pressure? So they're all connected. So let's do a sample of how we would use the ideal gas law. We might want to know, we might want to find the volume of 3 moles of hydrogen gas at 1 atmosphere of pressure and 20 degrees Celsius. So we've got a gas at standard atmospheric pressure, and we want to know what's the volume of it. So we have PV equals nRT. So the volume is going to be nRT over the pressure. So the number of moles is easy. It's given. Ideal gas constant is also given. Incidentally, I should comment, if you've had chemistry, if you've seen this in chemistry before, you may have seen a different value for R if you're fresh on your chemistry. And that's because in chemistry, they often use different units. Instead of using joules, they use calories. And for pressure, instead of using pascals, they use atmospheres. So we have a different value in physics class than some chemistry classes. Now for temperature, the easy mistake is to put in 20 degrees C, but that would be incorrect. What should the temperature be?
To 93 kelvins.
Yeah, so we have to add 273 to make it into Kelvin. So it's going to be 293 Kelvin. And then the pressure, I would also make a mistake if I put in atmospheres. Okay, we need the metric unit. So the metric unit of 1 atmosphere is Pascal, 1.013 times 10 to the 5th Pascals. So we need kelvins, we need pascals, we need moles and joules and so forth. So this is 0.072, and the units for volume in the metric system should be cubic meters. So if you want to know in liters, that's going to be 72 liters. You guys get the same number that I got? Anyone work that out? Just to double check me. I got the same thing twice, so it must be right. Okay, so that's one use of the ideal gas law. We can fill in, if we know the other variables, we can fill in that missing variable. Maybe we know the volume, pressure, and temperature, and we want to use that to find how many moles there is. But what we more often use the ideal gas law for in this class is to see when we change one thing, how does something else change? So for example, if we said 4 liters of a gas at 20 degrees C and 1 atmosphere is heated to 200 degrees C at 1 atmosphere. What is the new volume? So in this case, I don't know what kind of gas it is or how many moles. So it might seem, if we are sort of still stuck in the I need to get numbers for everything up front to start working, we might feel like we can't do anything. But in fact, we can work symbolically and still answer this question. So the way I would do it is I would think of the pressure P1 is 1 atmosphere, and the pressure P2 is also 1 atmosphere. And the volume, the initial volume V1 is 4 liters, and the volume V2 is what we're looking for. And the temperature T1, that's 20 degrees C or 293 Kelvin. And the temperature T2, well, 200 degrees Celsius converted to Kelvin, we add 273, so this becomes 473 Kelvin. Now, number of moles, don't know what it is, but it's not going to change whenever we're heating up the gas because it's just how many particles we have. So what we do is we write the ideal gas law. This is a trick, but it's a trick we'll use a lot. We write it twice, one on top of the other. And then we put 2's on the first equation and 1's on the second equation. So we're writing down the ideal gas law for, time 2 or situation 2, and then we're writing it again for situation 1, and then we divide these equations. So what this does for us is it cancels out the ideal gas constant and the number of moles. They both just disappear. And in this particular case, because P1 and P2 are the same, well, heck, we can cancel those as well. So what we have left is just V2 over V1 equals T2 over T1. So we can solve this algebraically for V2. V2 will be equal to V1 times T2 over T1. So that's 4 liters. Now, I didn't really need to convert to cubic meters because my units, I just will wind up with liters at the end. 4 liters times T2, which is 473, over T1, which is 293. And that turns out to be 6.46 liters. Dalton.
How did we get to 473 Kelvin again?
So we have 200 degrees Celsius. How do we turn that into Kelvin?
Add 273?
Yes. So 273 plus 200 is 473.
Okay. I guess how did we get the first temperature then?
Well, I thought you were the one that told me that 20 degrees C is the same as 293 Kelvin.
Oh, I see. Okay. All right. Thanks.
Okay, you're welcome. So I asked you though that on the last problem, but I just used it since we last problem had 20 degrees C. I just used that. We had already worked out that that is 293 Kelvin. Okay, great, good questions. Any other questions?
Yeah, so will we always just assume liters, or when do you want us to do the other way? Or like convert it, or?
Yeah, it will depend on the context and what you're trying to find. So if I'm given liters and I just want to find the new volume in liters, then, or it's not specified, I can just go ahead and stick with liters. But if I'm using the ideal gas law not as a ratio, so here in this problem I'm doing a ratio, and so I'm kind of canceling stuff and I'm getting the V2 in terms of V1, then it doesn't matter so much. But in this earlier problem, because I'm not doing a ratio and the units of everything are not canceling out, then I have to be careful. Okay, so I guess when you're doing ratios, things like these pressures being in atmospheres, they just cancel out anyway. So I never like had to convert them. And even if it had been 1 atmosphere and 2 atmospheres, I would have had 2 atmospheres over 1 atmosphere, but the atmosphere part would just cancel. So with these ratios, we can be a little bit more flexible with our units. But I would say whenever you're not sure, just go ahead and convert to the metric base unit just to be on the safe side. Okay, any other questions? All right, last thing, what if we had a problem where they didn't exactly tell us the number of moles, but they said we have 5 kilograms of O2 at 20 degrees Celsius and 2 atmospheres of pressure, has what volume? So they told me how much stuff, but they didn't exactly give me the number of moles. So here's where we kind of need to know a little bit from chemistry class. So if you don't know this from chemistry class, that's okay. You'll be provided with this information, but it may be a little bit unfamiliar vocabulary, okay? So what we need is we really need the periodic table of elements. If you look on the periodic table of elements, you're going to see the atomic weight of oxygen. It is 16 grams of oxygen per mole. So we need access to this number. This is called the molar mass in this class, capital M. It's 16 grams per mole. That would be 0.016 kilograms per mole. So we need to look that up. That is not a number that you should have memorized. It's a number that ordinarily we would look it up on a periodic table of elements, but on our textbook problems, I think typically it will just be given so that you don't have to look it up. On the contest, for sure it will be given, okay? So you don't need to know the periodic table of elements and how to navigate it and how to find stuff, but you do need to kind of know what this means. So there are 16 grams per mole for the element oxygen, but because this is diatomic, O2, you get 2 atoms of oxygen in each molecule, then we have to multiply this by 2. So it's really going to be the molar mass of O2 is going to be 0.032 kilograms per mole. So you can think of this as a conversion factor between kilograms and moles. So if I have 5 kilograms, I can multiply it by, 1 mole over 0.032 kilograms. Just like we're converting units, we're using this to convert the kilograms into moles. And that's 156, I'll just round it there, 156 moles. Okay, so that's just an extra step that sometimes we have to do because the problem doesn't give us the information the way we would like it. So now we can use PV equals nRT and solve for the volume. That's nRT over P. So the N is 156. And the R is that constant 8.31. Of course, that's given to you, on a contest. And the temperature, we have 20 degrees C, but just like the last two examples, we want to convert that to Kelvin. So that's going to be 293 Kelvin. And then we divide by the pressure. So the pressure is 2 atmospheres, but we want to convert that to pascals. So that's 2 times 1.013 times 10 to the 5th, because that 1.013 times 10 to the 5th, hopefully you've been practicing enough with the fluids that you've kind of internalized that pressure. Of course, it would be given to you on the contest, but just hopefully you recognize where, what it is. So that's an atmosphere. Then we multiply it by 2, and that is 1.87. Again, the units, because we're using metric base units, then the volume has to be the metric base unit, which is a meter cubed. And if we wanted in liters, we could use the conversion factor, 1,000 liters per cubic meter to convert that. It would be 1,870. All right. Any questions? Okay. So let's take this statement and try to make it an equation. What exactly are we doing to get the number of moles? We're saying the number of moles is equal to the mass divided by the molar mass. Okay, so that's a handy little relationship. If we have a mass of some stuff in kilograms, okay, then we want to divide by the molar mass in kilograms. If the mass is given in grams, we can use molar mass in grams. But the key is to get the, number of moles, we take the mass divided by the molar mass. What if we wanted to know the density of some stuff then? You've got a problem or two in your homework that asks you to find the density. So how does that factor in? Well, density is mass over volume. So let's rewrite our ideal gas law. PV equals nRT, but the number of moles is mass over molar mass. So to get the density, that's mass over volume. I see the mass over on the right and I see the volume on the left. So what I want to do is move that volume to the left on the denominator, and I want to move everything else that's attached to the mass to the right. So we're going to multiply by the molar mass. Divide by the volume. And then to complete it, we're going to divide by the R and the T also. So we have molar mass times the pressure over R times T equals mass over volume. So that's equal to the density. Okay. Now, I wouldn't think of this as an equation. This is not an equation that I will provide on the contest. Instead, you should kind of be thinking, how did I do this? How did I get to density from the ideal gas law? Well, basically, density is how much stuff divided by the volume. So we're dividing the N by the volume. And then we have to replace the N with mass over molar mass to get, you know, what we really want is mass over volume. So just, you're going to have to practice that a little bit with a few of your homework problems. But you have it in your notes to refer to kind of help you see how to do it.